In first few lectures we shall derive or we shall make my students accustomed with the mathematical concepts which will be required for the subsequent development of the topic electricity and magnetism. As in the first lecture we have discussed the different forms of the integral theorems of vectors and the definition of divergence, gradient and curl in terms of integrals. In this second lecture we shall discuss the decomposition and uniqueness theorem of a vector field. The decomposition theorem actually deals with the fact that given a vector, how can I dissolve it into components and write the different components as in terms of potentials, the scalar potential and vector potential. On the other hand, the uniqueness theorem gives you what are the minimum conditions that are to be specified in order to define a vector field uniquely. We start with the decomposition theorem. We consider a vector field A such that a vector field A is finite, well-waved, in a volume, well-waved everywhere. Furthermore, A together with its surface integration A goes to 0 as r tends to infinity together with surface integration of A dot ds as limit r tends to 0 goes to 0. That is to say that the vector field A this is not 0, this is infinity asymptotic region. That is, the vector field A falls off sufficiently high rate so that in asymptotic region the vector field and its surface integration vanishes. And we consider a region, a finite region bounded by a volume V prime and a corresponding closed surface S prime. The original vector is defined in this, and we want to calculate it at some other points. So first thing is that given any vector A at a point R, it can be decomposed into two parts. One is its longitudinal part and other one is its transverse part. By longitudinal part, if we consider this is the point, then this is the longitudinal component of A, while this gives you the transverse component of A. So this is the longitudinal component. This is the longitudinal component, and obviously it is the longitudinal component, so divergence of AL is not equal to 0, but since it has no circulation, curl of A has to be 0. Divergence of A is not equal to 0 and curl A is to be 0. And this is the transverse component, and since it is along this transverse direction, it has nothing to flow out, so AT is equal to 0 and curl of AT is not equal to 0. This relation immediately suggests that AL can be written as the gradient of some scalar point function. By convention we put a minus sign, and this immediately tells us that AT can be written as curl of some scalar vector point function beta r. So we write this is minus alpha of r plus curl of beta of r, where alpha is called the scalar potential. This is scalar potential corresponding to the vector field A, and beta is the vector potential. So as per decomposition theorem, we can write the any vector A into its component, longitudinal and transverse component. Longitudinal part can be written in terms of the source of A, that is can be written as the scalar potential, and scalar potential which is related to divergence of A, that is it signifies the source term, and this gives you the vortex term. Our aim is to find alpha and beta in terms of A. So to this end, so we shall finish the theorem where we shall establish the relation is that alpha of r is equal to 1 upon 4 pi and beta of r, sorry. Let us now first explain the symbol. If we consider any point within this, we call it as the source term. So we call it as prime coordinate. This is the source coordinate. And if we calculate the vector A at some other point, this is called a field point, and this is the vector R. Relative coordinate is equal to r minus r prime. This is source coordinate, and this is the field coordinate. In entire electricity and magnetism, we shall abide by this notation. So, and r is the relative coordinate. So, our objective is to show that any vector A can be written in this form. To achieve this relation, we use a vector identity, which is we shall use a vector identity like this. Curl of curl B for any vector B can be written as minus B. We call a special B is that is equal to A of r prime by r dv prime integrated over v prime. So we apply this vector theorem, vector identity, to this vector, so that we get curl of A r prime by r dv prime integrated over v prime is equal to divergence gradient of dv prime minus which we write as curl of T3, this term we call it T3, this term we call as T2 minus T1. You see that T1 is this part, it is a vector. So T1 is a vector which is T1. T3, it is another vector. T3 is this part. And T2 is a scalar. Our aim will be to calculate these terms separately. First, we shall calculate terms one after another. So first we consider the evaluation of the term T1. So T1 is here consider that the differentiation is with respect to the source coordinate, and integration is with respect to the field, differentiation is with respect to the field coordinate and integration is with respect to source coordinate, which are independent of each other. So we can interchange the order of integration and differentiation. So we write this relation as integration over v prime you notice that nabla, when written in Cartesian coordinates, it represents del 2 del x2 del 2 del y2 del 2 del z2. So these are the functions of field coordinates, but A is a function of source coordinates, so nabla does not operate on this, and we get A at r prime now note that r is r minus r prime as for this picture, so that if we write it in Cartesian components, it is x minus x prime plus j cap y minus y prime plus k cap z minus z prime. So r square is x minus x prime whole square plus y minus y prime whole square z minus z prime whole square. If we differentiate it with respect to x, then we get twice r del r del x, since r depends on 6 quantities x, y, z, x prime, y prime, z prime. We are using the concept notation of partial derivatives, and this is twice x minus x prime, which gives us del r del x is equal to x minus x prime upon r. Similarly, del r del y, we will have y and y minus y prime in the numerator. Note one thing, del r del x prime will come out with a negative sign because of this relation. Now we are to calculate terms in this. We are to calculate del 2 del x2. So first let us calculate this, which we write as del r of then del r del x. This part is minus 1 by r square and then x minus x prime by r, altogether minus x prime upon r cube, which leads to the case that divergence of r. If we calculate similar components, y and z component will lead to the fact that grad of 1 by r is equal to minus r by r cube, which we did. Now our aim is to calculate the second derivative. So we need to calculate second derivative, that is del 2 del x2 of 1 by r. Del 2 del x2 of 1 by r is del x of x minus x prime by r cube with a minus sign. So on differentiating first term we get minus 1 upon r cube, and then the third part, this part on changing of variables, we get 3x minus x prime square by r to the power 5. So that we have to add two more such components, so this will get minus 3 upon r cube from there, and this term will be added to 3r square by r to the power 5. This is equal to 0 if r is not equal to 0. But what happens to this where if capital R happens to be 0? When capital R happens to be 0, this cancellation of r square on the numerator divided by r to the power 5 on the denominator is not possible, because division by 0 is not allowed in mathematics. So what to do? So we'll see that nabla square of 1 by r has a very high value at capital R is equal to 0. This is apparent from the fact that the numerator goes to 0 square form and the denominator goes to 0 in the form 0 to the power 5. So there is a very high peak of the quantity at r is equal to 0. Indeed, we shall see in our forthcoming classes that this is related to delta function. But here we shall arrive at the result in a slightly bit different way. So our objective is that if capital R is not equal to 0, the integration is 0. So this integration can be effectively converted into a integration over tau a r prime 1 by r over tau, where tau is a volume. This is a tau, very small volume around the source point, and it is connected, bounded by a closed surface sigma. Since we are considering the case where r prime and r, vector r prime and r are 0, so we are from this extended volume we are switching over to a very small volume tau, where tau tends to 0. And we try to apply the vector theorem over there, and in which case when r and r prime are same, we do not anymore require to distinguish between prime and unprimed coordinates. Furthermore, since the volume is very small over which A doesn't have any appreciable change, so the quantity A can be taken out of the integration sign, and we write it as this T1 is written as A at R times integration over tau, now plus square 1 by r integration over tau, where tau tends to 0 is a tau tends to 0. It is v prime tending to 0, and we write it as A of r this volume integration is converted into a surface integration. Note that this is not prime, this is R. And this is a closed surface integration sigma now if for this part we write minus r dot sigma vector was missing rq. So this is the solid angle subtended d omega is r dot d sigma by r cube, and the total solid angle subtended at a point is 4 pi, so the result is minus 4 pi A at r. This is the value of A. T1, sorry, T1. So T1 is with a minus sign. So this T1 is a minus sign, and T1 comes out to be minus 4 pi A at R. So first term has been evaluated. It is directly related to the vector field A. So we keep this is equal to minus 4 pi A at R. Now come to the calculation of T2. The term T2 as is apparent from this, T2 is a scalar power, is a scalar quantity. T2 is a scalar quantity and is equal to divergence of A r prime by r dv prime integrated over v prime. The differentiation is with respect to field coordinate, integration above with respect to source coordinate, so we can interchange, and we write it as now again this is the function of source coordinate, so nabla doesn't operate on it, and we get Now this part is 0, so we have at this point we cannot use vector theorems because because of the fact that differentiation is with respect to the source coordinate and differentiation is with respect to field coordinate and integration is with respect to the source coordinate. So we cannot use vector theorem. To use vector theorem, we must bring both the integration and differentiation on the same footing. You cannot convert the integration over source coordinate into that of a field coordinate, except the case we discussed in connection with Q1. So what we can do, we can change the differentiation with respect to source field coordinate into a source coordinate. So the nabla, the integration differentiation with respect to field coordinate is del x plus similar things, and nabla prime is equal with respect to del x prime. And we see in other case that for a given value of r, we see that del x is related to minus del x prime, so that we can write it as a minus integration over v prime nabla prime of 1 by r dot a of r prime dv prime. Now we write this as minus integration over v prime this has two terms. One is the term this, another term is this is prime. We can convert this one into a surface integration, and we get the result is that this is minus sine integration over s prime and this 2 minus n makes it plus Now coming to this surface integration, say this is the volume V prime, and where the source means divergence of A and curl of A are non-zero only in this region, and outside this region divergence and curl of A are 0. That is, the source and vortex term persist only within V prime, and V prime is bounded by the surface S prime. We add up a area over it. So the area, then we call it V double prime bounded by S double prime. The region beyond V prime and within V double prime, in this case, here the both divergence and curl of A is 0. So in fact, this part does not contribute anything to the integral, but in using the vector, if we take this surface to S double prime, if we consider this integration, we can convert it into V double prime integration, in which case this part will be converted into S double prime part, and we can take S double prime to lie far away. And as per the proposition A field and its vector A and its surface integration goes to 0 in asymptotic region. So this is 0 as S double prime tends to infinity. So we are left with the only term thus. So this can be written as now upon integration what we'll get, we get a quantity which depends only on r, vector r, because the prime coordinate has been integrated out over a finite volume, and we call it as 4 pi alpha of r, where alpha of r, the scalar point function, is defined as 1 upon 4 pi integration b prime. This is the alpha, the scalar potential part. Now let me say once again what we have done in T2. First, we have interchanged the order of integration and differentiation, as the integration and differentiation, one with respect integration over source coordinate and differentiation over the field coordinates are independent of each other. Then we have used the vector identities. Basically, we have used the vector identity, that is divergence of alpha A is equal to alpha times divergence A plus grad alpha dot A. This is the vector identity we have used, and since divergence field differentiation with respect to field coordinate does not operate on A, which is the function of source coordinate, we get this relation, and then to enable us to use vector theorem, we have replace the differentiation with respect to field coordinate to a source coordinate, and again use this vector identity, and finally we have used the divergence theorem to convert this part into a surface integration. We have used a trick on surface integration. We have added up a volume where there is neither any source nor any vortex of for the field A, so this contributes nothing to the integration T2, but we can convert the integration from S prime to S double prime, where S double prime can be taken to lie far away from us, and at very large distance both the function vector A and its surface integration goes to 0 as per our precondition. So we are left with only this term, and this term, that is the T2 term, reduces to this, and when we perform a definite integral over the source coordinate, we are left with a function of field coordinate, scalar function of field coordinate, which is the scalar potential. The same technique will be applied to evaluation of the term T3. Only thing is that here it is divergence operation. For T3 we will have curl operation. So we are performing the calculation in a similar spirit. So T3 calculation. Now we interchange this, and this does not operate on A prime, so we will have here we have used the vector identity that curl of alpha A is equal to alpha times curl A plus grad alpha cross A. This term doesn't contribute, so this term is kept over there. And we interchange the order of differentiation, so we shift from source differentiation from the field point to the source point, and we write it as, so again this is B prime was missing. Curl of it has two terms. One is this and other term is adjusted like this. Now this part can be converted into a surface integration.
Hello, Moto. Hello, Moto.
We have converted the here we have converted this surface volume integration into the surface integration using one of the alternative form of Stokes theorem, which is this. And again, taking the surface integration from S prime to S double prime, we can set it to be 0, so we are left with only one term. So this is upon integration, the quantity is a vector quantity which is a function of r only, and we call it as 4 pi beta of r. We call it 4 pi beta of r, so that beta is equal to 1 upon 4 pi integration v prime So this is the final result. So let me come back to first, before going to this, T3 is equal to 4 pi beta of r, where beta is given by this form. So we come to this relation. Now let us write the term one by one. This relation gives T3, curl of T3, so 4 pi curl of beta is equal to T2. T2 is 4 pi alpha, 4 pi grad of alpha, and coming to minus T1. Minus T1 is, there is a minus, so this is 4 pi A of r, or we get A of r is equal to minus grad of alpha of r plus curl of beta of r, where alpha is given by this relation and beta is given by this relation. So this is the decomposition theorem, which enables us to write a vector as its longitudinal and transverse component, where the longitudinal part is related to the scalar potential and the and the transverse component is related to the vector potential. In the case of electrostatic field, now we come to some physical situation where we can apply this theorem. Now we see that alpha is given by the divergence of A. For electric field, E. For electrostatic field is defined as divergence of E is equal to rho and curl of E is 0. So, rho by epsilon 0, and this is since curl of E is 0, the vector potential is 0. So this denotes that beta is a null vector, and since divergence is non-zero, the alpha is not 0. This is the electrostatic scalar potential or gravitational potential, magnetostatic field. Magnetic field is characterized by the fact that divergence B is equal to 0 and curl B is equal to minus del E del T. So since divergence B is 0, the scalar potential is 0. This gives you scalar potential is 0. So there is no magnetic scalar potential in general. Since divergence B is
Hello, Moto.
that B can be written in terms of a vector potential. B can be written in terms of a scalar potential. Vector potential. Since divergence B is 0, the scalar potential is 0, but we have a vector potential since divergence curl of B is not equal to 0. For electrodynamic field, we have both curl E is equal to minus del B del T, and curl B is mu 0 J plus del E del T. It is related in this case. In this case, both the curls are non-zero, and subsequently we will have both scalar and vector potential. In fact, for electromagnetic field, electrodynamic field, E can be written as minus grad phi minus del A del T, where this is the scalar potential and this is the vector potential. So this is the all about decomposition theorem. In the next class we shall start uniqueness theorem.